All right, so as promised, I'm going to do these next two. They involve some fractions, so hopefully we'll get some good review at fractions. But again, we're trying to validate, does a certain solution point satisfy the given equation? We already know that x comma y, just by the equation, right, satisfies it. But what happens if I replace y with negative y, right? That basically establishes if I'm symmetrical about the x-axis. What happens if I replace x with negative x? That's talking about being symmetrical about the y-axis. And if I make them both negative, right, I'm basically doing my rotation or double flip. So if I can show that these points are actually solution points to that, I've proven that they're symmetric about the x, the y, or the origin. So let's begin. So to do the x-axis, I'm going to basically take my equation and I'm going to replace my y with, I'm going to replace my y with negative y. That's all I need to do, right? X is still x, but y is negative y. So to try to get back to the original equation where y is by itself, how about I multiply both sides by negative 1? All right, and if I do that, we obviously get y on this side, but over here, be very careful, right? We're multiplying by negative 1, so that's negative 1 over 1. And so this becomes negative 6 over x squared minus 9 after my horrible writing. And if we take a look, right, we got y by itself now, but what it's equal to, right, is not the same as what we originally had. So this is not equal to, so the answer is no, right? We're not symmetric with the x-axis. Okay, so if you were to bust out your graphing calculators, you would see that there's no mirror image about the x-axis. What about the y-axis? Well, we're going to go to our function. Y is still itself, but the x is being replaced by its opposite. All right, and so can I get back to the original one? Well, y is y, 6 is 6. Squaring a negative is the exact same thing as squaring a positive. And so if we do the math, right, we find that what I have here actually does, right, represent what I started with. So the answer here is yes, right? If I take the opposite of x, I end up with the same equation that I solved. So xy is a solution point, and negative xy is a solution point. Symmetry about the y-axis. So gold star as far as this guy's concerned. What about the origin? Well, they both are negative, right? So I'm going to replace y with negative y. I'm going to replace x with negative x. And we're going to see if we get the same thing back. Oops, did that wrong. So that's negative y. Let me keep that there. This is x squared minus 9. You can already kind of see it coming. If I multiply both sides by negative 1, right, we get y equals negative 6, x squared minus 9. So that does not equal what we originally had. So if I replace both x and y with their opposites, I don't get a solution point to the original equation. I'm a solution point to a completely different equation. All right, so the answer here is no. So keep track of who you're taking the opposite of. For the x-axis, if we're symmetry, then the y is basically opposite. If the y-axis symmetry, it's the x's that are opposite. If it's the origin, they're both opposites. We're doing a 180-degree rotation or double flip. So last but not least, right, here we've got 4x over x squared plus 1. And I'm first going to try to prove again. We already know that xy satisfies that equation. But does x negative y satisfy it? If it's a solution point, we're symmetric. So if I go through and I replace my y with negative y, doing some math, right, because I want to get back to y, I would multiply both sides by negative 1. Remember, negative 1 is over 1. We get y equals negative 4x all over x squared plus 1. So here's what we've got. Here's what we started with. They're not equal. The answer is a resounding no. We are not symmetric with the x-axis. Okay? What about the y-axis? Well, to test it, we're going to replace x with negative x. So I go to my original equation, and I replace my x with negative x. And when I do the math upstairs, we get negative 4x. Squaring a negative is the same thing as a positive. And so that's about as far as I can take it. All right. Oops, that's a plus 1. I'm doing the last problem. I'm sorry. All right. So we basically get that. If we compare what we have to what we originally started with, they are not equal. So the answer is again no, right? So this graph, whatever this graph is not symmetric with the y-axis. What about the origin? Well, here we're going to replace both x and y with their opposites. So if I do that with my equation, we get that, right? Let me clean this side up first. We get negative y equals, the top's a negative 4x. Squaring a negative is the same thing as a positive, right? Now handling the y, right? I want to go back to y equals, not negative y equals, so I'll multiply both sides by negative 1. Keep in mind that's upstairs. Negative times a negative is a positive, so there's my y. A negative times a negative is a positive, there's my 4x. X squared plus 1, right? Because that times 1 is itself. That is equal to that. So the answer here is yes. We are symmetric about the origin, so gold star for that one. So this equation, 4x over x squared plus 1, actually does have a nice symmetry about the origin. All right, double flip or a 180-degree rotation. Again, I'll let you guys go to your graphing calculators and visually see what I algebraically have proven. All right, and again, as I keep reiterating through this, even though we have technology in our hands, it's nice instant gratification. What I'm showing you algebraically actually builds up more math. We'll talk about even and odd functions and all kinds of neat stuff. But if you don't understand what's happening algebraically here, you're going to have trouble, right, building some understanding mathematically later on. So please, please, please use your technology to verify what you're seeing algebraically. Now it's become the good tool that it's supposed to be. Alrighty, we got one more topic to discuss in this section, and then we're done. I will see you then.